So now let's do the chi-squared test on our TI-83s. We have our probably not independent but potentially independent data that we observed, and then we had this expected value chart, and this expected value chart being different than this doesn't prove that it's not independent. We want to know how different it would have to actually be. So the way that we're going to rephrase this situation is into two hypotheses, a null and an alternative, just like we have with many other statistical tests. Since we want to know if the type of animal and number of fur colors are independent or not, the null is to assume that they are, in fact, independent. So let's take this one step at a time. Our null hypothesis that the type of animal, number of fur colors are independent. That's our null. There's no symbols or anything in the chi-squared test for our null and alternative. You can just write it out in words like this. The alternative then is the opposite, that they are not independent, that they are dependent. So the type of animal and number of fur colors are dependent. That's our alternate hypothesis. We still have to choose an alpha level just like we do in any other statistical test, and typically 0.05 is going to be a good choice for that, although there's always exceptions to that rule. To do the chi-squared test, we're going to focus on the middle of the table. So we don't need to worry about any of the labels on the outside. We don't need to worry about any of the margins. We only need to worry about the middle. So step one is going to be to take out our calculators and put all of these numbers here into matrix A. Now to find matrix A on a TI-83, make this a little larger here, we're going to go to second x to the negative 1 here, second matrix, and we're going to go to edit. So when we choose edit, we're going to be given a matrix. Now the way it's broken up here is first number of rows going across, then the number of columns going up and down. If you forget, if you make a mistake, let's say you do this, you see that it's a 2 by 3 and you do it in the wrong order, no big deal, because you'll notice that it makes your table in the wrong way. In this case, I actually did it right by accident. So if you were to do it wrong, you would clearly see what you did wrong. So we have 2 rows, 3 columns, and we want our grid to look something like this. So to punch in our values, we would have 75, 33, and I have some of these values already in there, and then 12. We have 53, 45, and then the last one going across would be 14. And you plug all these values into your matrix A. You just type them right in. Once you have that, your second step is to actually run the chi-squared test, which is pretty simple on the TI-83. All you do is you go to Stat, you go to Tests, and you work your way up from the bottom to go to C. And chi is a Greek letter. It looks like an X, so that X squared looking thing is the chi-squared test. Don't do D, the GOF, or goodness of fit test. That's a little bit different. We're going to do the standard chi-squared test. Here it says observed is A, that's matrix A, which is what we want. The expected is B, matrix B. We don't actually have to type anything in there. It will calculate it for us. It's just going to put it there in B. And then we just have to calculate. And when we do that, this is what we get back. I'll drag this over. So chi-squared test, our chi-squared value is 5.5119, etc., etc. That is a value that we won't really use much. That's just internal to the test. And then the important one is the p-value, 0.0635 and so forth. Now, when we do p-values and we get something very close to 0.05 but not quite, we unfortunately fail to reject, which is too bad, but we would have a strong suspicion that there's probably a link there. Our data is very close. So we might want to collect more data and do a retest in the future or something like that. So we did our first 2 steps. We put our data in matrix A and we ran our chi-squared test. We got our p-value and all that. But now we have to go back and make sure that the test was actually valid. To do that, we have to check matrix B. for some minimum values. Most of the values in this table we're going to look for to be 5 or more, and all of them have to be 1 or more. So to look through this, we go back to second matrix, we go to edit, and we go to B this time instead of A. And looking at the values in here, we see that all of these values are in fact more than 5. 66 is way more than 5. The only one that even comes close here is this 12 and 13. Both of them are above 5. If those numbers were below 5, we would start suspecting that the test might not work. At least 80% of the different cells here, so in this case at least 5 out of 6, would have to be a 5. If you had one of them, let's say we had something here and it was a 1.5, that would be okay. You're allowed to have 20% of them be smaller like that, less than 5. But if it was too small, let's say it was 0.78, then that would not count. Then we would have a bad test and we would have to go back and say that this test was not valid. So this minimum conditions is making sure we have at least 5 of everything except maybe 1, and at least 1 of everything, no exceptions there. Last step is if we do find a significant p-value, we go back to matrix B and try to figure out what caused that major discrepancy. So to go back into our calculator here, if we look at the values, we see that 66 and 75, they line up to the same spot, are about 9 apart. So I might jot a little note to myself to say that those two values are 9 apart. And you can repeat this with all the values. 60, let's call that 62 and 53, also about 9 apart. It's only coincidence that these two numbers are the same. Typically you'll find differences there. 40 and 33, we're looking at about 7 apart. 45 and 30, let's call that 38, would be about 7 apart. So again, a little bit of coincidence that these all happen to be the same here. And you can go through, these are about 1 apart from the expected value in the table. And what you're looking for is which of these are the greatest differences from expected, and not just as a number, but often as a percentage. Because if all the numbers are big, you would expect it to have more deviation. Whereas here, these smaller numbers being a full 7 away, that's a pretty high percentage away. So what we're trying to figure out here is what caused this major difference? What caused the break from independence? And if I had to pose a theory, I would say that none of them are particularly strong, but in this case, the two-color cats and dogs both seem to really be quite a ways off of what we expected in independent situations. So it seems like the number of two-color animals are not quite what we would have expected to see. That would conclude the chi-squared test. So you put your data in, you get your p-value, check that your minimum conditions were met. If they were, you can continue and try to figure out what caused the difference. If they were not met, then you would just throw out the test and say you are not allowed to do the test.